Well, hello and welcome again to our journey into linear algebra, and we've been looking at the Jordan form. We've seen so far a number of examples of 3 by 3 matrices in the various different situations that can occur. The main one we looked at to start with was when you have one eigenvalue and geometric multiplicity of that eigenvalue is 1, and then we looked at other situations as well. So just a little bit of theory without any proofs here. We've seen by examples how the chain method works for several 3 by 3 matrices. What can we say about the general case? Is every square matrix similar to a Jordan matrix? Well, we state the following results here. Little lemma: if A is a square matrix and lambda is an eigenvalue of A with algebraic multiplicity m, means it has a factor of x minus lambda in the character to the m in the characteristic polynomial, then the generalized eigenspace corresponding to lambda also has dimension m. So the geometric multiplicity may be less than m, but the dimension of the generalized eigenspace is exactly m. And that's a very nice and very important fact. The generalized eigenspace for lambda then has a basis with m vectors in it, consisting of vectors which can be arranged into one or more chains, where we start off with one vector v sub k and we keep multiplying by a minus lambda I until we chain our way into the eigenspace. So v1 is an eigenvector, and the generalized eigenspace will have a basis consisting of such sequences of vectors. Now, the proofs of these facts are difficult, and I'm not going to do them here. You need to look in more advanced books on linear algebra to see all the technical proofs of these. As you might imagine, they're not trivial, and our main theorem is that every square matrix then is similar to a Jordan matrix. And that is a very interesting and very important fact. Every square matrix is similar to a Jordan matrix. And a square matrix is similar, moreover, to only one Jordan matrix, except, of course, the order of the blocks can be varied. You can put the blocks in a different order and you get what looks like a different Jordan matrix, but of course it's just the same thing. So exactly as happens in the diagonalizable case. Now, any Jordan matrix similar to A's we're going to call a Jordan form of A. Now, since the Jordan form is essentially unique, it gives us a test for similarity as to when two matrices are similar. Now, remember, we say that A is similar to B means that there is a matrix P, so that P inverse AP equals B for some matrix P. Some invertible matrix P. That's what we mean by similar. Another way of saying it is that we can change the basis with respect to which we have the matrix A, change the basis, and then with that change of basis, the linear map represented by A has matrix representation B. Now, the point is then, our next theorem says that two matrices are similar if and only if they have the same Jordan form. So underlying every square matrix, there is a Jordan form that's giving us all the information about that particular matrix. So two matrices similar, but they have the same Jordan form, except, of course, possibly for rearrangement of the Jordan blocks. Now, that's very useful because, for example, if I take these two matrices here, these matrices turn out to have the same trace. We can see the trace of each of these is 6. They've got the same determinant. They've got the same eigenvalues. And so you might suspect, well, they've got everything so similar, they must be similar, matrices must be similar to each other. But in fact, they have different Jordan forms, and so they are in fact not similar matrices. You can't change the basis with respect to which you have this matrix and turn it into this one. These matrices are not similar. And the only way of telling that is to look at the Jordan form. So the Jordan form is a very useful thing there as well. We'll see it getting used a bit later on in a later section when we look at systems of differential equations, and we'll find that when we get to non-diagonalizable matrices, the Jordan form again plays an important role. Now, we've done this so far for 3 by 3 matrices. You can just about do it by hand for a 4 by 4 matrix. For larger matrices, it's often computationally difficult, at least by hand, to find the P matrix. And in many applications, we're often only interested in the Jordan form. After all, if we want to check when 2 matrices are similar, we don't need to know what the P matrix is. We just need to know the Jordan form and not the P matrix at all. So a couple of little basic results which you possibly may have guessed as we've been doing some of the examples here, or seem to be that should be true. The diagonal elements of J are of course the eigenvalues of A, and they're repeated according to algebraic multiplicity. So in each of the Jordan blocks making up the Jordan form, the eigenvalues are repeated in each block according to their algebraic multiplicity. The sizes of the Jordan blocks are determined by the lengths of the chains of the generalized eigenvectors, and hence by the nullities of these matrices A minus lambda I to the k for each of the eigenvalues and for various values of k. And finally, the number of Jordan blocks associated with lambda is equal to the dimension of the eigenspace E sub lambda. And that's because if you think of the onion, when you each of the linearly independent eigenvectors in the eigenspace is the end point of a chain. So the number of linearly independent eigenvectors is going to correspond to the number of chains, and each chain builds a Jordan block. So just to finish with a couple of examples of this, we're going to look at a big matrix now, a 12 by 12 matrix. I'm not going to show you what it is. We're going to just imagine we have a 12 by 12 matrix, A, and it's only got one eigenvalue in this case. Lambda is 7. And what you're given here is you're given the dimensions of the various kernels. So the dimension of the kernel of A minus 7i is 4. That, of course, is telling me the number of eigenvalues, number of eigenvectors, I should say. And that, of course, will tell me the number of Jordan blocks in the Jordan form of A. If we go to the next kernel out, if we take A minus 7i and square it and look at the kernel of that, that's got dimension 7, and the next kernel out's got dimension 10, the next kernel out's got dimension 12, and that's as far as we can go because we've only got a 12 by 12 matrix, so this will give me all of the 12 linearly independent generalized eigenvectors. And we're asked to find the Jordan form of this one. So here's a worked solution to this. So we start off with our 12 by 12 matrix. Lambda is 7, and there are the various dimensions of the various kernels. Now we can represent this information in a couple of ways. We've been using the onion, and the onion's still nice to draw here, but there's also a thing called a block diagram, which is another way of representing the same information. So looking firstly at the onion, the innermost kernel is 4. That's the number of eigenvectors, and there are I put 4 crosses here to indicate the 4 linearly independent eigenvectors. When we go to the next kernel out in the onion, then the dimension of that space is now 7, and that means we've picked up 3 more generalized eigenvectors. So we started off with 4 eigenvectors. We now, at the next kernel, we've got dimension 7, so I must have picked up 3 more. The next kernel out has dimension 10, so we pick up 3 more generalized eigenvectors in that space to span that space. And then finally with 12, we pick up 2 more to make up the 12. Another way of representing that is to use this block diagram, where we've got dimension 4 in here, so we put 4 crosses here. We pick up 3 more to make up the 7, pick up 3 to make up the 10, and then 2 more. Block diagram can be more useful in this context because it's easier to draw. And the point is now, going back to the onion, when we build our chains, we would pick say this vector here, and we would chain in, and we'd build a chain of length 4, and that corresponds to a Jordan block of size 4, and that corresponds to this here. So that will build me a Jordan block of size 4 based on 7. And then we take this vector and we chain into the center. That would give me another chain of length 4 corresponding to a Jordan block of size 4. And then we have one of size 3 and then one of size 1. So that gets me the Jordan form of the matrix, or you can get it from the block diagram, and that is, once we've looked at the dimensions here, we look in this direction to get the chains. So a chain of length 4 corresponding to this one, chain of length 4, chain of length 3, chain of length 1, and there's the Jordan form of the matrix. As a second example going the other way, we've seen that how to find the Jordan form of the matrix A if we know the nullity, the dimension of the kernel of these matrices for the various lambdas and k's. So conversely, if we know the Jordan form, we can work backwards and we can work out the dimensions of these things. And so, example here, if A is similar to a matrix J, which has this as its Jordan form, so it's got a block of size, 3 blocks of size 2 based on the eigenvalue -4, a block of size 3 and a block of size 1 based on the eigenvalue 1, then we can write down these nullities. And here's the worked solution to that. Here's our example. We have our matrix A, which is similar to the matrix J, and there's the matrix J as we were given. So we're going to do this for each of the 2 eigenvalues. So for lambda equals -4, we're looking at the first 3 blocks here. Now we've got a Jordan block of size 2. That means we have a chain of size 2. So we're going to do the chains firstly this time. We have another Jordan block of size 2, which came from a chain of length 2, and another one, a chain of length 2. And then we can get the kernels by looking at it in this direction. So if we look at this, this is going to give me the dimension of the kernel of A plus 4i. That's going to be 3. This is the 3 eigenvectors of the matrix. And we go to the next kernel out, we pick up 3 more, which gives me a total of 6. And indeed, if we were to calculate any higher power, if you kept going and calculated the cube, the fourth, and so on, any k bigger than 2, then you don't get any more, you only get your 6. Then we do the same thing for lambda is 5. So for lambda is 5, we've got a chain, block size 3, so a chain of length 3, and a block size 1, chain of length 1. That's the chains in this direction, and then we look at the kernels this way. So the innermost kernel's got dimension 2. There are 2 eigen vectors, and then we go to the next bit. We pick up an extra one here. So we have a Jordan block of size 1, I should say. So we've got our chain of length 3 here and a chain of length 1 here. And now looking at the kernels, we've got 2. We pick up 1 more to give me 3, pick up 1 more to give me 4. And again, that won't get any bigger. So if k is bigger or equal to 3, that's going to stay at 4. By the way, this tells me that this must have been a 10 by 10 matrix, because we have 6 generalized eigenvectors here, 4 generalized eigenvectors here, giving me a total of 10 generalized eigenvectors. So A must have been, in fact, a 10 by 10 matrix. And that's all we're going to say about the Jordan forms. We'll come back and look at these or use them again in a later section when we start looking at systems of differential equations.